All right, there we go. We're going to finish up chapter 7 today, and I suspect that our class will actually be pretty fast because we did part of it on Monday, and I think that we are pretty confident in what we're doing. So now I said that, that means that it will be a long class, right? All right. So we're going to finish up chapter 7. Remember, we're talking everything you ever wanted to know about matrices. Hi, hey, Sarah, how are you? We're going to talk everything you wanted to know about how you can use matrices. Yay, matrices, right? Greta likes them. Howdy. So on Monday at the end of class, I said one of the things that you can use to find out or to use matrices and the determinant of a matrix is you can find the area of a triangle. So remember, the formula is that the area of a triangle equals plus or minus 1/2, and then the determinant of each of your coordinates written out in a matrix with a third column of 1. So that just sounded like a bunch of words that I just said, but that's, sorry, what we got going on. So let's try one of these out. What is going on today with my computer? All right, so we got that. We need a problem. Let's go ahead and do the one with a, ugh. Well, let's do number 6, sure. I did number 6, so we'll be all right. All right, so we got this lovely picture of not a triangle here, and we're going to use the area of a triangle to find, I know it's blown up, but at least we can see a little better. We're going to use our area of a triangle to find the area of this not so triangle, right? What do you notice about this triangle though? So let's see. This is at -4, 4. This triangle goes from -4 to +6, so that's 10. Here it goes from -8 to +2, so that's 10. All right, and the vertical piece, this goes from 1 to -3, which is 4, and this goes from 4 to 8, which is also 4. So when you, on further inspection of this not-so triangle, you should notice that if you have a tool to draw a line, if you draw a line from this point to this point, you actually make 2 congruent triangles. Okay, they are rotated and stacked on top of each other, but they're actually 2 congruent triangles. So now we can actually use this handy dandy area of a triangle formula and find the area of one of the triangles and add it to the area of the other triangle. We could also, if we're skeptical, we could find the area of each and add them together. So that might not be bad practice either. So if I wanted to find the area of this purple triangle here, what is going on today? Everything I click today is just not working. So if I want to find the area of the purple triangle, we would say that the area equals plus or minus 1/2 the determinant of my x1, y1, and then some number 1. So we know all these are going to be 1. It doesn't really matter which one is your x1, y1, which one's your x2, y2, which one's your x3, y3. So we're going to put our points in. We've got -4, 4. We've got 6, 8, and we've got 2, 1. Okay. So for time purposes sake, and since you don't, excuse me, and since we spent a ton of time on Monday talking about finding determinants, let's go to desmos.com/matrix, not matrix. Okay. And let's find the determinant of that matrix. So we have a new matrix. It's a 3 by 3. Okay. we have coordinates at -4, 4, 1, 6, 8, 1, and 2, 1, 1. So that's our matrix. If I want to find the determinant, the det of A, I get that it is -54. And that's okay, because remember my formula is that the area equals plus or minus 1/2 times the determinant, which is -54. So in order to get a positive area, I'm going to go ahead and pick the negative here, right? And I will end up with the area of the purple triangle equals 27, right? What about the area of the green triangle? The area of the green triangle is similar, right? Area is plus or minus 1/2 times the determinant of these points. So I've got -4, 4, 1. I've got 2, 1, 1, and I've got -8, -3, 1. So I'm actually just going to be a little bit lazy here, and I'm going to take my matrix and I'm going to change the one row that's different. So it's -8 and -3. I should have had this over further. So what you see, like if I put -2 in here, the determinant changes based off of this, but this is -3. So that determinant actually happens to be the same thing because these two triangles are congruent to each other. So the area of the green triangle is also plus or minus 1/2 of -54, or the area is 27. So if I add together the green plus the purple, I get that the area is 54 units. All right. So this area triangle rule, pretty cool, especially if you get to use a matrix calculator to find it, right? We could find the determinant, again, by using either the technique where we list out all of the determinants and we multiply down and multiply up and add them together. Or we could use cofactors, which is where we kind of break the matrix up. Or we could use a matrix calculator. It doesn't specify. Okay. Any questions on that? Pretty easy, right? If you look at problem number 7, it says, hey, Connor, I cannot click any of the right buttons today. It's just been one of those days. What? There we go. If you look at number 8, that's what I'm trying. There we go. If you look at number 8, it says, find x such that the triangle has an area of 4 square units. Dun, dun, dun. So if you were trying to do number 8, right? How would you do number 8? So what we could do is we can set this up using our matrix. So we know that our area is 4 units, right? Area equals 1/2 the determinant of your matrix. So the area equals 4 times 1/2 times our matrix, which happens to be -4, 2, 1, -3, 5, 1, and -1, some unknown x, and 1. So we know that that all has to equal to 8. So in order to solve this equation, what we do have to do is we have to figure out what is the determinant, and we can't use a calculator for it, which is probably why they give us this problem, right? So what I would do is I would probably use the add up and down method, which is this. So I'm going to find this determinant, right, by using this method. -4, -3, -1, 2, 5, x, 1, 1, 1, -4, -3, -1, 2, 5, x. Okay, so if I multiply down, right, -4 times 5 times 1, -20. Then I have 2 times 1 times -1, so -2. And I have -3 times x. It's all negative in the bottom. Okay, when I go up, I have -1 times 5 times 1, so I get -5. I have x times 1 times -4, so -4x. And I have 1 times -3 times 2, so -6. Let me make my paper bigger here. So if I take, I have -20 plus -2 plus -3x. And then I'm going to subtract everything in blue. So it's minus a -5, so it's +5, minus a -4, so +4x, and minus a -6, so +6. All right. All of that, that's your determinant. Multiply by 1/2 equals 4. Okay. So what I'm going to go ahead and do is I'm going to, instead of making this multiply by 1/2 equals 4, I'm going to make this 8 equals all of this. So I'm just going to multiply by both sides by 2 just to make my life easier and not have that fraction there. Okay, so I need to simplify. I have -3x and 4x, so I just get x. And then I've got -20 and -2, so -22 plus 5, so that's -17, plus 6, which is -11. Did I do that right? -22. Yeah, -22 plus 11 is -11. So I'm going to add 11 to both sides and get x equals 19. That doesn't seem right. Let's double check my math. How can I double check that I did it right? So I could always go into Desmos and put my matrix in. So I have -4, 2, 1. I've got -3, 5, 1. And I have -1. What do we get? X equals 19. Oh, I'm off by 1/2. What did I do? Oh, no, that works. Okay. So if x equals 19, the determinant is 8, and the area is 1/2 of 8. All right. So that's how you deal with a triangle. All right, the second case is the even easier case. Okay, so that's your area of a triangle. The second one is to test if points are collinear. So I think it was Sarah. Sarah, you were like, I know what collinear is. They all are on the same line, right? Back from geometry. So if 3 points are collinear to each other, if and only if, when you put them into a matrix and you take the determinant has to equal 0. If you have 3 points that are on the same line, and you put each of those points into a matrix and then add 1 to your third column, or make your third column all 1, you take the determinant and it will equal 0 if they are collinear. So this is one of those things that is pretty easy to use. All right, so if I have these points here, for example, doesn't matter. use a determinant to determine whether the points are collinear. All right, so let's take number 12. Sure, let's take number 12. All right, so if I wanted to tell if the points in number 12 are collinear, right, I will make a matrix with the points. So I've got 0, 1/2, 1, 2, -1, 1, and -4. I think that's 7/2 and 1. So if I take that determinant and it equals 0, then these points are collinear. So if you would like to find the determinant by hand, you can do that. You could also use Desmos to do that if I can get them all in the same spot. So I've got 0, 1/2, 2, -1, right? And -4, 7/2. Okay, so when I take the determinant of this matrix, it equals 0. So I could then say that these points are collinear. Also, if just to kind of wrap it all together, if you graph these points, they should look like they're on a line, right? You might not be able to completely verify it just by visually, but these should look like they are on a line. Oops. Yes, 1 point, 2, -1. Telling me I can't type today. -4 and 7 divided by 2. Okay, so if you graph those 3 points, blue, red, green, they look like they are on a line, but our matrix has verified that they are indeed, in fact, collinear. All right, pretty easy. I think it's pretty easy. All right, the last thing is probably the most complex, and that is something called Cramer's rule. Okay. So let me read this box to you. I know it's very exciting when I read things like that. Cramer's rule says if a system of n linear equations in n variables has a coefficient matrix A with a non-zero determinant of A, the solution to the system is x sub 1 equals the determinant of A sub 1 over the determinant of A. And then there's a bunch of different things there. This is one of those rules where I actually think it's easier to see how Cramer's rule works. And then I can tell you why I think it's good and what I think the upside and the downsides are. Okay. So again, we are back to solving a system of linear equations. Back again. I can't get away from, right? Algebra 2, solving systems of linear equations. We did it in pre-calc. You know, got to know how to solve these systems of linear equations. When you take linear algebra, someday you'll get to solve systems of linear equations. So this is how Cramer's rule works. Okay, so what you're going to do is you're going to take and this is different than what we did in algebra 2. All right, so Cramer's rule works like this. First, we're going to make some matrix A that represents the coefficients in front of our x and our y. So I have 4, -3, 6, 9. So I'm pulling the coefficients out in front of my variables, and I'm making a matrix. I'm going to then take, take the determinant of that matrix. Okay, we can do that pretty easily without a calculator, right? Because that's just 4 times 9, which is 36, minus -3 times 6. So the determinant of matrix A happens to be 54. Yes, 54. 36 plus 18 is 54. Okay. So to apply Cramer's rule, what you do is this. If you want to find out what is x, okay, You want to find out what x is. What you're going to do is you are going to, this is the weird ace of one thing. You're going to take, so you're trying to find out what x is. So instead of putting 4 and 6 in for x, you're going to put the solutions in. You're going to put -10 and 12. Okay? And then your y's you're going to leave alone. So you're going to put in -3 and 9 because we're trying to find x. So we're going to leave y alone. Okay? And then you're going to divide that by the determinant of A. So you have to define the determinant of this new kind of weird matrix and divide it by the determinant of A. So the determinant of the top matrix is going to be -10 times 9 minus -3 times 12. And then we're going to divide that by the determinant of your original matrix, A, which is 54. So -10 times 9 is negative, this becomes basically -90 plus 36 over 54. -90 plus 36 actually happens to be -54 over 54. And so we get that this equals 1. So this tells me that x, my variable x, equals 1. Okay. So then if I want to try to find y, you're going to do the same process. So y, you're going to divide by the determinant of the original matrix. Remember, your original matrix came from your x and your y's. Because you're trying to find y, you're going to replace out your y's. All right, so your matrix is going to be 4 and 6. The x's stay the same. Okay. But instead of your y's, you're going to put in the solutions, which are -10 and 12. Okay. So again, we can find the determinant. It's going to be 4 times 12 minus -10 times 6 all over the determinant of A, which is 54. So this becomes 48 plus 60 over 54. And if you do the math, you get 108 divided by 54, which is 2. So y equals 2. So the solution to that equation is -1, 2. So yet another way to solve a system of linear equations, right? Long, long ago, when you first saw this, you thought the only way was substitution. And then we learned about elimination. And then we learned in Algebra 2 about using the inverse. And this is called Cramer's rule, which is a different way to do it. So there's lots of different ways to do it. I'm partial to finding the inverse. Like I like the Algebra 2 method better. And I want to show you that really quick just because it's my favorite. No, just kidding. Just because I think that it's good to know all the different ways. Because there are lots of different ways, right? This is Cramer's rule that I just showed you. Just to review from Algebra 2, because I'm kind of sad that your book doesn't do it. You can take this, sorry, you can't even read my original equation, but you could take this and turn it into a matrix. So you can say this is 4, I think, I have my paper here, 4, -3, 6, 9, right? Times some matrix xy equals -10, 12. Again, this is not in your pre-algebra or pre-calc book, but this is in your Algebra 2 book, and I thought it's a good method, right? So this, if I take, this is matrix A times some matrix X equals matrix B. If I multiply matrix A by the inverse of matrix A, then I also need to multiply matrix B by the inverse of matrix A, and I get to solve. So X equals the inverse of matrix A times B. So this is powerful because if you do have a matrix tool, remember, you can just put these matrices in and do the problem. So let's delete this matrix. How do I? There we go. New matrix, 2 by 2. And it is going to be 4, -3, 6, and 9, if I can type right. Right? That's your one matrix. Your new matrix is going to be a 2 by 1, which is -10 and 12. And your solution is going to be take matrix A, the inverse, and multiply it by matrix B. And your x is -1 and your y is 2. So like I said, I just like that method because I think it's nice and clean and it makes sense to me, like the idea of taking the inverse and solving the matrix like you do an equation. But I do want to let you know that there is that way of doing the Cramer's rule where you use the determinant to find your matrix. Okay. I also want to let you know that I am fine on number 15 through 21. It says use Cramer's rule to solve if possible. Maybe try one with Cramer's rule, but if you would like to solve it using this method, I'm okay too. So you could solve it with either method. Especially for number 21, I would recommend this method. So, does anyone need to see another example of anything? The area of the triangle, collinear points, or Cramer's rule? Or do you think you have enough to try it on your own? Anybody? Another example? You done?
I think I got it.
You got it? You're good? All right. Well, then I will let you guys work on your homework and get that done, and I will send out the test. And like I said, everything will be due. Let me look at my calendar. The 18th. So if you have any questions on Monday, make sure you bring them in. We can still go over them. But I think you guys should be able to do it. All right, guys. Thanks for coming. Have a good rest of your week and rest of your day.
Thanks. See you Monday.
Thanks. See you Monday.